Thank you very much for a nice introduction. I would also like to thank the organizers for organizing this nice workshop. It feels very nice to do something physically with people. Yes, so this is, as mentioned, is a joint work with Yoshihito Kazashi and Fabio Nobile. So Yoshihito is actually now in Heidelberg, so he's not anymore with us in EDPFL, but yeah, this we worked together in EDPFL, and then Fabio, he's my supervisor. This will be the outline of this talk. Yeah, it's a talk on dynamical low rank approximation. We have seen a nice talk on this topic already yesterday. So this will be a bit more from a discretization perspective. So I will introduce the method again, and I will propose some new discretization schemes. And basically then we will, and then I will talk about like three main properties for these particular schemes, which include stability analysis, a priori error estimation, a posteriori error estimation. So first I state the problem. So we will have two physical separable Hilbert spaces H and V, and they form a Gelfand triple. We will work in a time interval 0 to big T, and then the underlying probability space will be denoted by omega. And this is the problem we are trying to solve. So the true solution satisfies this equation here. This is a random time-dependent problem. Now the randomness can arise from the initial condition, from the forcing term, or from the operator L. Now the operator L will be assumed to be linear and elliptic. So this is a parabolic equation. And we are looking for an approximation of that equation in this form. So we have a mean value here, and then we have the sum of R terms, which are composed of two modes. We have deterministic modes and stochastic modes. Now this can be somehow viewed as a reduced order technique because this R will be small. R is fixed in time, and if we were to compare it to some other other more standard reduced order techniques like POD or polynomial chaos expansion, well, in POD our deterministic modes are fixed in time, and we evolve the stochastic coefficients. On the polynomial chaos expansion, our stochastic polynomials are fixed in time, and we only evolve the deterministic coefficients. Now, this is kind of basically a generalization of those two, where we allow all of these terms to evolve in time, and basically we need to have evolution equations for all of these terms. With this notation star, I'm going to denote the zero mean part of every random function you will see in the talk. Now, so we have this R. This rank are fixed in time. So we are looking for R rank approximation. And basically, we want both of these to be linearly independent. Now, we can have, with this condition, we can have infinitely many choices for our modes here, which still give us the same function U. So we need to prescribe some further, some more constraints on our modes. And basically, standardly, we work with three choices. There is something which is called dual DO, in which you have the deterministic modes linearly independent and the stochastic modes orthonormal. This linear independency can be also equivalently expressed as the matrix consisting of all the scalar products in H of deterministic modes to be full rank. Then you have something which is called the DO form, where you have deterministic modes orthonormal in H and stochastic modes linearly independent. And then you have this double DO or bi-orthogonal, in which you have deterministic orthonormal and stochastic orthonormal, but you still need to evolve. Okay, here is supposed to be T. You still need to evolve in time this matrix S is a matrix R times R, and this matrix is then full rank. Basically, if people are familiar, for example, with the work of a group around Professor Lubich, they work with this form. Now, in our work, we have the dual DO form, in which, as I said, the stochastic ones are orthonormal. They are zero mean because we put the mean value here, and then the deterministic modes are independent, or yeah, this matrix is full rank. And then we have the corresponding dynamically orthogonal condition, which prescribes evolution for the stochastic modes, and is this one. So the dynamical low rank approximation has a nice geometric interpretation. Basically, By MR, we denote the set of all functions which are which are R-rank functions with the form I said, I prescribed, and I mean this set of all these functions forms a manifold, and basically we are looking for approximation which lies in that manifold. Now here I have it said with the basically. Since I put away the mean value, all of these notions are in the zero mean setting, but it's just like a detail. And then we have an easy expression for a tangent space at a certain point, and we also have an easy interpretation for the projection on the manifold, and also for the projection on the tangent space. So this is the formula for the projection on tangent space. I pointed out because we will use it later. So we have this projection on the Y subspace, and then we have this orthogonal projection on the Y subspace of projection on the U subspace. Okay, and basically the idea behind the whole method is that instead of evolving U dot equal to F minus LU, we evolve U dot equal to projection at U, projection on tangent space at U of the operator. So basically in the original equation, this operator here would take us generally out of the manifold. Now we project it on the tangent space. We evolve in the projected direction, and basically infinitely for infinitely small, very local in time, it keeps us on the manifold. And this can be written in a DLR variational formulation in this way. So basically we have the same equation as we would have for the true solution, but now we only test it with functions from the tangent space. Okay. So we have a smaller set of test functions.
So excuse me, can you just comment on exactly what orthogonality you have here? Because there is the L2 row, so it is the orthogonality in the stochastic sense, and then there's also the orthogonality in the space sense, so in the V and H, and in space-time. I mean, so what, when you say projection and
yeah, so it's a projection in the L2 row omega H. Okay,
my ambient stochastic sense. So in
it's both stochastic and space. So this ambient space is basically L2 row of omega H. So functions, random functions grow into omega with values in H.
And pointwise in time.
Yes.
Okay, thank you.
Okay, so with this idea behind, we can derive equations for all of the terms that we have in the expression we need for the approximation. So first we have an equation for the mean value. So it's a deterministic equation, right, for the mean value. Then we have R deterministic equations for the deterministic modes. Now here is this term where basically we are projecting on the Y modes. It's just something we will have to deal with when we'll try to discretize. And then we have a system of R equations for the stochastic modes. Now here we have the projection on the deterministic modes, okay? Then we have this projection on the orthogonal complement of this space Y. And we have this matrix M. So all of these are some kind of terms we'll have to deal with later. Okay, so well, we have equations for all of our quantities. Now how we obtain a discrete solution. So that's the next part of this talk. So for the spatial discretization, we work with a space VH, which is a finite dimensional subspace of V, and basically we perform a Galerkin projection, and we assume that we have some kind of inverse inequality in our subspace VH. Yeah, I mean for well, you would have P would be equal to 2 if you have to find elements, but we just did like P. Maybe you can have something more general at some point, but it's like just standard inverse inequality.
Okay.
Yeah.
Between V and H.
Between only in VH, and then this is V norm and H norm. Yeah, like normally we would have H10 and L2.
Yeah.
Yeah.
And then you will have just H.
Just H. Yes, sorry. Yeah, squared is squared. Yes, right.
Okay. Thanks.
Okay. And then stochastic discretization is performed. We use a discrete measure which is given by a finite number of collocation or sample points and weights. And now, so we have n hat of them, and these weights need to be non-negative. So basically work with either Monte Carlo or tensor grids. And then the time discretization. So we are looking for a solution at the new time n+1, which is given by a new mean value, finite dimensional, and the new deterministic modes, finite dimensional, and the new stochastic modes, which when they are evaluated in these sample points here, are basically functions in R and hat. And then we have the discrete orthonormality conditions and discrete mean value. And the new solution is obtained by this scheme. So this is discretization for the mean value equation. So we are taking test functions from the finite dimensional subspace. Yeah, and then we have, well, this is for the time derivative. And then we have, so mean value is computed as a sample mean that will hold for all of the mean values that appear in these equations. And then this term here is a symbolic term by which we mean that the operator L can be evaluated either in the old solution or in the new solution or in some kind of combination of them. And then the same for the forcing term, so either it at n+1. Okay. Now for the deterministic modes. So basically everything is similar to before. We have the sample means, we have the finite dimensional, we have these functions from the finite dimensional subspace. And then this projection on the stochastic modes. So we consider the old stochastic modes. So in this step, we are computing the new deterministic modes, but we use the notion or the knowledge of the old stochastic modes. So if this term is evaluatable, this is completely computable at this time. And then we have the system of R equations for the stochastic modes, where now we take, so this matrix M is obtained using the newly computed deterministic modes. Then this projection on the stochastic complement is obtained using the old stochastic modes. And now here again, we have the new obtained deterministic modes. So it's basically like a time marching scheme. You can go one by one. And then as a last step, we orthonormalize in order to obtain orthonormal new stochastic modes. So here I try to highlight the fact that we are using old stochastic and new deterministic, and this will be important, and we will see why.
The mean L star, it is the...
It's the always taking away the mean value.
Yeah, but the L is the adjoint, or is the...
No. It's you evaluate L in either one of these, let's say, and then you take away the mean value.
Okay.
Yeah.
Yes.
Mm-hmm.
Thanks.
So to see why basically doing the projections in this way is important, we introduce analogous geometrical objects, but in the discrete setting. So we have again the set of all R rank functions, but now in the finite dimensional space, the same for the tangent space. And then we have the same for the projection. So here again, we have projection on the Y subspace, projection complement on the Y of projected U, of projection on the U. And now I'll try to explain why this was important. So just when taking the equation for the deterministic modes, if we multiply it by Yn transpose from the right-hand side, we see that here we obtain this projection on the Yn of our operator. Okay. Now we go to the system of equations for the stochastic modes. So before here I had this matrix. So let's say I can invert the matrix. I inverted it here, and then I multiply the equation by U tilde n+1 from the left-hand side. And basically what we can see here is this projection on the U tilde n+1 of our operator, and then further projected on the complement of Yn. And now maybe it's already, here you can already see that this is giving us the projection, as a projection on tangent space at a point formed by old stochastic, new deterministic. And now if you just sum these equations together, you basically have an equation for the zero mean part of your new solution, because this combined new deterministic or stochastic is, when you sum it, it erases. So you just end up with zero mean part of the new solution minus zero mean part old solution, delta t, And then we have this projection of your operator on the stochastic subspace plus projection complement of projection of deterministic subspace. So it's as I said, projection of tangent space formed by these points here. And here I need to point out that this property is not, I mean, it is obviously easy to show, but it's not straightforward for any other type of time discretization of the terms here. Like if you were to do, if you were to do projection on all deterministic here, you would not get this property, right? So, yeah, I mean, if you do it in this way, you can write the discrete variational formulation, which says that, which is stated in the following way. So you have the, I mean, yeah, new solution minus odd solution. Then you have this operator evaluated, the symbolic operator, and you are taking test functions from this tangent space. And this is basically the key property which is used for stability analysis, a priori estimates, and a posteriori estimates, because well, it basically simplifies all the analysis. And yeah. So now I just proceed with the stability analysis. So first I recall some standard stability properties for a true solution that we would try to see also in the discrete DLR solution. So, so basically you can bound the H norm at the final time step of the true solution plus integrated in time V norm by H norm of the initial condition and integrated in time forcing term. And then in fact, completely the same estimate holds for the continuous DLR solution. So this is interesting because like without any discretization considered, you don't really see any DLR-ness in this estimate, right? It's yeah, you have a DLR solution, it satisfies completely the same stability estimate. And basically that's something we would maybe like to see also in the discrete DLR versus maybe, yep. Okay, yeah, CL is a coercivity constant of the operator L.
On the V, on the space V.
Yes.
So it's independent of the rank, right?
Yeah, yes. Yeah, it's just a coercivity constant of the operator L before you start with any DLR approximation or anything.
Okay.
Yeah. And basically, when trying to show something similar for our discrete DLR solution, we use two main ingredients. Is the discrete DLR approximation, discrete variational formulation, and the fact that actually both the new and the old solution, they belong to the tangent space. So we can use them as test functions in this variational formulation. And now I will go on and basically I will specify the operator evaluation and then state stability properties for the specified scheme. So we introduce an implicit scheme in which the operator is evaluated in the new solution. So basically, this scheme completely couples the modes. You cannot go and compute mean value, then deterministic, and then stochastic. All of these are coupled together. However, it has the nicest stability properties, of course. So we have an analogous result which bounds the error in the H norm at the final time plus integrated in time V norm by the H norm of the initial condition and integrated in time forcing term. And basically, this is the same stability estimate you would have for just applying implicit Euler on your equation. So again, you don't see any DLR-ness in this result at all. Then, yes?
We're thinking here of linear elliptic operators, right?
Yes.
Okay.
Yeah.
Okay.
And since we're already asking, then I might ask my question, which I've been asking myself. Am I to think basically of the theta method, or are you thinking of more complicated time discretizations as well? It's just the theta method, linear combination of the two values.
Okay, so here you can.
No, I know. Now it's Bakodola, but before it was any theta method.
Here you can do anything, honestly. Here you can do any. To have this discrete formulation, you can do anything. Okay, this is
any Runge-Kutta, implicit Runge-Kutta, anything you mean?
Yes.
But you need implicit stages and something.
I'm sorry?
You need then stages in between. So I'm asking, are you only thinking of the theta method where you take a linear combination of those two values, or are you thinking of more general? implicit or explicit schemes?
Okay.
Explicit is only when it's one of them.
Okay, I will tell you. I think you could do anything, but I want to think a bit more. Okay. But I think you could do anything.
But your time step is fixed, right?
I'm sorry. Time step.
Time step. Your delta t parameter is fixed, right? It's not.
Well, now I'm only working between Tn and Tn plus 1. Theoretically, you could have different time steps between different. Like for now, all results are only between n and n plus 1. So this can be time dependent. Anything else? Yeah, I wanted to have this comment later, but I can also say it now. Like just for the discrete formulation, this operator L does not need to be linear and does not need to be elliptic, in fact. Okay. So this just this result holds for also nonlinear and non-elliptic. Yeah. Okay. I mean, you can see. I mean, the proof is really just this slide. So anything you can do.
Yeah, that's why I was asking actually. Yeah, okay.
Like, yeah, if you can do this, you can do.
Yes. Okay, thank you.
You need coding inequality or some coercivity.
Yes, you need coercivity.
But you need coercivity, but not for the discrete formulation. You need coercivity for all of these three. Yes. But just for this result, you don't need coercivity.
No, this is just discretization.
Yeah, yes, exactly. Yeah. Okay.
Yes, thank you.
Okay. Here, yeah. So explicit scheme. I mean, I guess so. Quite expectedly, it decouples the modes. Now here, if people are familiar with the very well-known projector-splitting integrator, which is a popular technique, for the full rank case, they are equivalent. And then under CFL standard parabolic CFL condition, we have this stability estimate. And again, this is the standard CFL condition you would have for explicit Euler without any DLR approximation involved, and also the result. So again, we don't see any DLR in this result. And then for a specific, then we have one more scheme which is basically suited for this case of random heat equation, where the domain D, so we have a physical domain D, then V, H, V dual are these spaces of H10, L2D, and the dual. So our probability space is parameterized by a finite number of random variables, where M is the number of them. And then we have so with the heat equation, we have a random Laplacian where the diffusion coefficient is random. And in fact, it's affine with respect to random variables. And I will denote this term by A stoch. So we have the mean value part and the A stoch part. And it is uniformly bounded from W to below. And well, this is the standard random heat equation we are trying to solve. So for this case, we propose a semi-implicit scheme, which treats the mean value term implicitly and the stochastic term explicitly. And this scheme is nice because it decouples the modes. You can go and compute first the mean value, then the deterministic modes, then the stochastic modes. And then under standard CFL, under easier CFL condition, you have an analogous stability estimate as we had before. And then, in fact, if L is symmetric, which is the case for the random heat equation, you can have this type of estimate in the energy norm, where by energy norm, I mean this norm here with the gradients and the diffusion coefficient. So basically, you have so it's an estimate for you have estimate in the L norm, which requires no conditional time step. So, well, all in all, you have a scheme which decouples the modes and is unconditionally stable. And then I have some numerical results, which basically support the theory we derived. So if you work in a two-dimensional domain and a two-dimensional stochastic space, so we have this equation here. We have 0 forcing term. So what we would like to see is decrease of norms. Our initial condition is of rank 3, and we also keep the rank 3 throughout the evolution. Basically, we use tensor grid with 81 Gauss-Legendre collocation points and P1 find elements. When applying the explicit scheme, this is the result we would like to see. So basically, when the CFL condition is satisfied, the norms decrease. And well, so in the first case, the condition was satisfied and the norms they kept on decreasing. Then we took half of the spatial discretization parameter and consequently 1/4 of the time step, and the norms kept on decreasing. And then if we try to violate the CFL condition, so we only took 1/3 of the time step, at some point the solution exploded. And then we tried all kinds of, all kinds of spatial discretization parameter and the time step. And basically here in this graph, by the blue dot, I'm denoting that the norms kept on decreasing throughout all the evolution. And by the orange dot, I mean that at some point the norm exploded. And you can really observe this nice KH square curve. So the condition is strict. And for the semi-implicit scheme, we would like to see decrease of norms for arbitrarily large time step. And basically that's what we observed. Like we tried many types of time steps, and however large that we chose, and it was always decreasing. So yeah. Yeah, and then I just have these comments here. So yeah, as I said, the discretion formulation holds for more general operators. Don't have to be linear, don't have to be elliptic. Now, there is a discrete variation formulation which holds also for rank deficient case, because in this DLR business, you always have the problem like you have the metrics there, you need to invert it. And then people are like, okay, so if your solution becomes of lower rank, you run into troubles. So in our scheme, we solve the problem in a least square sense, but in fact, so the solution with the singular the equation with the singular matrix there has infinitely many solutions, and whichever solution you would take, all of these solutions would satisfy discrete variation formulation. So you would have all of the stability properties that I showed also for the rank deficient case. And for the explicit and semi-implicit scheme, we managed to show that a solution exists. I mean, in fact, infinitely many of them exist. You can always add something from the kernel of the matrix you need to invert, but the solution always exists. So, okay, and for all of this solution, you have the stability properties. Mm-hmm.
You had R is equal to 3. Can you just comment on, so if you change R?
Yeah, I could pick it however I wished. Yeah. In fact, so these results are published in a paper, and there we so since we wanted to somehow deal with the low rank, with the deficient rank case, we started with the initial condition which was at first 3, like I had, and then we picked R equal to 20. And I mean, the norms kept on decreasing, there was no issue. But yeah, yeah. It's a random choice, the number 3. And then, okay, and then for people who are familiar with the Projector-Splitting scheme, I want to say that, in fact, not the same, but a similar variational formulation and stability properties can be proven also for that solution. So it's just a small remark. Okay, so now I would go to a priori error estimation. Okay, okay. So these, yeah, basically these two error estimations is another way of showing how useful the variational formulation can be. So for this work, we have more specified discretizations. We apply finite element method with piecewise polynomials of degree smaller or equal than R. Then we use the Monte Carlo method, okay? And then we assume these 3 conditions. So these first 2 conditions, they actually, so what they say is that the projection in the H scalar product, projection on tangent space in the H scalar product is stable in the V norm, okay? So this we need to assume. And then we have this low rank approximation condition, which basically tells you that the projection on the complement at this point here of the operator evaluated in that point is small. Is it related to the fact that when you are doing the projections on the tangent space, you don't want them to be too far away. You don't want the operator like close to your true solution to be far away from tangent space. So it's very related to the fact whether DLR method actually, it makes sense to apply it. And yeah, so this also needs to be assumed. And then here I'm just recalling the constants we are working with. And we can prove this theorem. So basically error at the final time step plus integrated in time error H error, blah, blah, integrating time, error in the V norm can be bounded by, so here we have error, which is caused by KL expansion, by KL truncation of the initial condition. Now KL truncation does projection on the manifold. Don't know if this was clear. And then we have these three terms here. So this comes from the spatial discretization. This is from the finite element method. And then we have this epsilon, which is the approximability condition we assumed. And basically all these constants, they are independent of smallest singular value. This is important because other standard types of a priori estimates, they always involve the inverse of the smallest singular value. So this is a property that holds for the particular scheme we are proposing. And so this holds for explicit and semi-implicit scheme, we need to assume the CFL conditions in order to have this, this standard. And then I go through like the main steps. So basically the two main ingredients, so you work with the variational formulation for a true solution and then variational formulation for your fully discrete solution. So here I have the projectional tangent space at this intermediate point. And then like the proof is very standard as you normally have without any dynamical low rank approximation. So you derive variational formulation for your error term. And then you end up with a term which accounts for the time discretization, error term which accounts for the space discretization, and then this projection on the orthogonal complement, right? Since we have the projections here we will work with the orthogonal complement. And like the challenge is to somehow manage to bound this. Well, it's quite simple. You just split it into two terms where you basically sum and subtract this operator L evaluated in the intermediate point. And here you apply the epsilon approximability condition. And then basically this term here can be quite easily bounded and is first order in time. So yeah, you just do this. I mean, the point of this slide is to show that usually these estimates, the proofs are quite difficult. So if you use this variation formulation, it becomes very simple. And yeah. And then we have an error estimate which accounts for the stochastic contribution. And basically, so if now I denote this set of all of my discrete solutions at those particular sample points, my probability space becomes this product space of omega. And I can derive an estimate of the stochastic error with respect to a Lipschitz functional, which takes a function from H and gives you a real value. And basically, so I denote by Mn this true mean value of phi evaluated in the true solution. And then I have Mn H rho is the sample mean value of the phi evaluated in the discrete solution. And you can bound the mean square root error of these two quantities. And then here you have the standard Monte Carlo error. And now, so this constant here depends on just some constants or the continuous norms of my data. And this is from the previous, basically this result is from the previous estimate, but now these constants, they don't depend on any discretization parameter. So you have all the stochastic error, time, space, initial condition, and the approximability one. Okay, and then, if people are not too happy with the condition on the projection, H projection in the V norm being stable. So in fact, if you would pose your problem in not the dual DO form, but in the DO form, so you would have your deterministic modes orthonormal in H and your stochastic modes linearly independent. You would when applying your scheme, you would first solve the stochastic modes, then the deterministic modes. And you can show an analogous variational formulation where now you have all the deterministic and new stochastic. So it's all very analogous, just they switch. And then these two conditions here are replaced by a simpler looking one, which requires the deterministic modes to be bounded in the V norm. So obviously they are bounded in the H norm because they are orthonormal, but now the condition ends up being that you want them to be bounded in the V norm. So it's just, yeah. And so last part is an a posteriori estimation. So this is suited for a random head equation where diffusion coefficient is affine with respect to random variables. And we apply, for space, we apply finite element method with triangulation TH and finite element space VH. And for stochastic discretization, we apply tensor grids with Gauss quadrature points. Basically, we obtain the discrete solution. So if here by U and H rho, I denote the set of all of my solutions in all the collocation points, they basically satisfy this equation for every collocation point and for every time n. Now here I'm allowing the time step to change in time, okay? And now basically having this, I introduce a discrete solution which is continuous in omega by interpolating these results for each collocation point with Lagrange interpolants. And then I interpolate in time my solutions which were obtained for every discrete time step. So basically this U tilde is a function which is continuous in x, omega, and t. And then I can proceed with a standard a posteriori estimation. And you can obtain this kind of estimate. So you have error at the final time, again in h, integrated in time, V norm is bounded by error of the initial condition. And then you have an error contribution, which accounts for the stochastic discretization, spatial discretization, time discretization, and rank truncation. Basically, so I'm not going to go through the formulas because they are a bit complicated, but I want to just point out that the spatial estimator can be localized for every element in the triangulation. The stochastic estimator can be localized for every dimension of your stochastic space. Now, for obtaining this, we use the fact that the diffusion coefficient is affine with respect to random variables. And then the temporal estimator can be localized for every time step. So this holds for the implicit scheme, and then something similar holds for explicit and semi-implicit, but yeah, you need to take care. And then the rank estimator looks complicated, but basically it's just bounding this term. So this is it's quite natural that the rank estimator will be derived by bounding this term, which is the projection on the orthogonal complement of the tangent space formed by the all stochastic deterministic basis functions. And this is your discretized operator evaluated in the intermediate point. So you need to have this and this here the same. And basically this rank estimator can be used to estimate the overall error caused by the rank truncation to R, but can be also localized in time. So you can have a different rank estimator for different time steps. And basically, yeah.
I believe. But this one, how do you then proceed? Do you oversolve a little bit every time? If you really want to use it in practice, do you oversolve a little bit with the rank and then cut back and have an estimate for a slightly smaller rank? And then, as with any adaptive method, you would still use the final one, but you have a rigorous bound for a lower R, or what's the practical?
So I have not implemented this yet, but I'm going to do it. But I think you would do like this, like you would proceed, count the error, then maybe change, proceed, count the error. If it's too
you need to do it obviously at the previous step, because otherwise you might lose something already before you even get to the next step. But anyway, I think I'll leave that for your next work. And then we'll read it. So.
You don't need to, right? Because in order to obtain this, I need to have a solution of this, so you probably need to do that. Yeah.
Thanks.
But, the important part is that you can use this to adaptively change the rank. You can change in time, so you can increase, decrease.
Rob's comment is more the type of algorithm that you're envisaging is one in which you change the rank from one time step to the other based on information that you have, or you rather run the whole simulation, you compute the error estimations for each time step, and then you decide whether to adapt the rank, and then you rerun the whole simulation in time.
So the first one is smart.
That's more difficult.
It's more difficult, but I guess that would be the choice, right? The thing is, you can do that. You can do it, so yeah.
I had a question.
Yes.
I think it was asked yesterday already by Christoph. So what if you had a formulation which was also variational in time, so that you had you make a weak variational formulation also in time. You have now a strong formulation in time, so you go step by step, and you would make a weak formulation in time. Then maybe this part with the changing the rank
would be
yeah. So you have combined. Now you have a combined stochastic and space discretization. That would be a combined space time and stochastic discretization, and then the rank could be included there. What do you think about that? I think the speaker yesterday was asked this similar question.
I don't think anything because I actually have never thought of that. But I mean, it's interesting, but I have no idea. I never even thought of that notion. Like
maybe we postpone questions for just a few minutes, and then you please continue.
I just have actually this last slide which concludes. So just to conclude the talk, so we proposed the new full discrete schemes for dynamical low rank approximation of random equations. Then we showed that these schemes satisfy this variational formulation, which is very helpful. And we showed some stability analysis for this particular scheme. For random parabolic equations, we showed some numerical results which support the derived theory. So the stability results are published in Numerische Mathematik. And then we also showed that this variational formulation can be used for further for showing these a priori and a posteriori error estimates. And I mean, that's all I have prepared.